In the academic university system, the people are represented by two separate yet equally important groups: the students who learn the material and the professors who teach it. These are their stories. Tong tong! Welcome back, everyone, and congratulations on making it through all the homework, as long as you actually did make it through the homework. If any of you want to improve your grade just a little bit, I'll mention now, and I mentioned in an announcement as well, that if you want to be able to do some older homeworks or past homeworks, I will reopen any of them that you send me an extension request for. But I have to see the extension request, otherwise I'm just not gonna, it's just too much work for me to go through everything. But if you want, and I'll write this down here. If you want to complete some old homework, send me an extension request. On WebAssign. So I'll approve any and all of those through Monday of finals week. So I don't want you guys doing any homework during actual finals time. So don't expect me to open them then. But that's just like a little tiny way you can raise your grade if you want. But with that, here we are on week 1 of final exam review. So I will be going through, I will have 4 practice exams, 4 total practice final exams. Eight problems each. The same will be for the actual exam. And you will have 20 minutes per problem for the actual exam. So these weeks, each of my lecture days, I will go through four problems from the practice finals. And you'll only see only two practice finals are going to be up this week, so I don't overload you guys. So you'll see 2 practice finals up this week. There are 2 practice finals up. You should have the first open. In conjunction with this lecture. Okay, so basically we want to open up practice final exam number 1. By the way, 120 times 8 is 160. Okay. So here we are on practice final exam 1. And this is day 1. So it's problems 1 through 4. I'm going to do my best to give you guys some background knowledge as to how to just think about these tests in total. So as we go through the questions, I'll kind of talk about the theory of the question, what you really want to take out of it. And it's not going to be like the very specific question itself. You want to kind of take a step back and say, what is this question trying to ask? And do I have a good comprehension of that material? You'll notice I've also changed the format from our last exam. I think when I wrote it down as explain something about the problem, that it was tough for you guys to parse. That was maybe too much of a linguistic mathematical statement, right? Like I was saying to do something in math, but I was saying it in English. So in this case, I'm just giving you a question and I'm giving you an answer, and then I'm saying, tell me why that's the answer to the question. And so you'll just basically have the answer sitting around that you can reference the whole time if you want to. So let's start with problem 1. Problem 1. And here we have question 1. There are actually 2 parts to it. So question 1 is d dx of gx cubed over hx squared. And I realize that the answer is given to you right there, but I think a good rule of thumb, I'm going to reference this right now. When you're completing these problems is don't look at the answer until you get stuck. And when I say get stuck, I mean after you've tried the problem once. Because preferably you're going to be able to solve this without looking at the answer. So in this case, we look at it and we see that there are functions and also expressions like cubes and squares. We also have a big line in the middle. But I guess maybe the theory behind, what is the theory behind this question? If you can't tell so far, the theory behind the question derivative rules. Right? This is basically asking you to show me that you know how to use derivative rules. And so when I look at this, I definitely see, well, let's write it this way. If this is a question about derivative rules, what derivative rules do I have to use? I'll either use the product, or I'll use the quotient, or I'll use the chain rule, or some combination of all of them. Can't spell all of them. So product, quotient, chain, or some combination of all of them. Here I certainly see a quotient. I hope everybody can agree. Since there's a fraction here, certainly use the quotient. So, will I use any others? Basically, I'm asking the question, what is going to happen with the gx cubed and hx squared term? Or what happens, yeah. with gx cubed and hx squared? That's a really good question. You want to identify that early on before you get too far into the mix. And it might not look like it, but these are actually gx, all in parentheses, cubed, and hx, all in parentheses, squared. And now, when we have parentheses here, parentheses, this is a great piece of theory to keep in mind. Parentheses equals chain rule, almost always. So we're also going to use the chain rule in these terms. Okay, so hopefully we can do that correctly. Let's try to do it. So we're going to try to take, I'm going to write it like this now. I'm going to say g of x, parentheses cubed, h of x, parentheses squared, prime. I'm going to start quotient rule. Quotient rule says bottom d top. I'm going to write it like this. That's how I'm going to write d top. Minus top d bottom. And I'm going to write d bottom like this. All over bottom squared. And squared squared, hopefully you guys can all agree with me on that one. It's h to the fourth. Okay, I'm not done yet though. Right? These primes here, I'm not done yet because I still have these prime terms. So I have to actually evaluate those terms out too. So let's do it. And this is where you can use the answer maybe to help you out. You want to know what those terms are going to look like. So let's just let's take an aside. Let's find both of these terms. The first one, g of x cubed prime. I said above, parentheses means chain rule, and chain rule means derivative of the outside. And the derivative of a cube is going to be, derivative of the outside looks like this. Keep the inside the same, multiply by the derivative of the inside. And the h term is going to look similar. So we found those two terms, and now we can sub them back in. So we're going to sub those in there, and what do we get? We get h of x squared 3 g of x squared g prime of x minus, up top here, g of x cubed and then there's a 2 h of x h prime of x. And then we just ask ourselves, does this does this look like the answer? Like the answer given? Yes, and if it does look like the answer given, that means we can be done with this problem. And this is really just part 1 of problem 1. But still. It looks like the answer, so we're good to go. And the above is a good explanation. So now we want to do problem 1. Problem 1 has a second question to it. Question 2 asks us to find d dy of the natural log of e to the y squared x minus y. Okay, here is a good teaching point. Professors like to be mean. Part of our job is to make sure that you pay attention to the whole problem. I should say that you bring a critical eye to every problem. Part of our job is to make sure you bring a critical eye to every problem. So this problem is written in a way to make your life hard if you don't spend some time looking at it. They're presented in a way to trip you up if you don't spend time. Trying to make it easier. So just think about it as like if somebody is walking along a path that they walk all day, every day, they know the path really well. But if it's somebody else's job to test whether or not they know the path well, that person might put a tripwire on the path, something that could trip the person up. Now, the person who's walking the path knows that the test is happening. So it would be silly of them to just walk the path like they always do. They should keep their eyes open for something that's a little bit tricky. And that's just what I'm asking you guys to do, is just keep your eyes open every single time, at least in math. The professor is going to try to change something very subtle and expect you not to notice it. And that's, kind of our job. You have to keep an open eye on this world. So that's what's going on here. The first thing is, what is the big thing here? Big thing here is that first piece says d dy. It says d dy, not d dx, even though there's an x in the problem. So how do we take a derivative with respect to y Well, you just treat y as the variable and treat x as a constant. Treat x as just a number. So y is the variable, x is just a number. So that's what you want to do in this problem. And I'll write it down again. We want to treat y as the variable and x as just a number. But I'm going to say we still don't want to try to take a derivative. We can still make this easy for ourselves. How? Log rules. These log rules, I didn't teach them to you guys just so that we could forget about them. We really want to keep those in mind. Log rules here. If I'm multiplying inside a log, that's the same as adding outside a log. So the multiplication on the inside is the same as adding on the outside. So now I'm adding on the outside. And what's going on here is that ln of e to whatever is just that thing. Ln and e cancel each other. And so since ln and e cancel each other, this is really d dy of y squared plus the natural log x minus y. And now it's easy enough for us to take a derivative. Now that it's easy enough for us to take a derivative, we just pretend like y is our variable. It doesn't matter in the first case. 2y is, of course, what we get there. But this other piece is a little tricky. So what does the natural log, how do we take a derivative of that? It's just the chain rule, right? You take this would be like the derivative of the outside is really 1 divided by whatever is on the inside. This is like the derivative of the outside part of chain rule. Outside, keep the inside the same. It's that part of the chain rule. And then multiply by the derivative of the inside. I'm going to write it like this. So we don't forget that it's x minus y, but we're taking the derivative with respect to y. So you get 2y plus 1 over x minus y. The derivative here, if I'm taking that derivative with respect to y, and I treat x just like a number, just like 6 or something, that's going to be 0 minus 1 times 0 minus 1. And all of a sudden I end up with 2y minus 1 divided by x minus y. And this is indeed the answer. It's the same answer we saw above. I'm going to circle this one up here. Forget that I forgot to circle it here. I always circle it. There we go. And so that answer agrees with what the sheet gave us, and then we're all happy. Okay, so that was problem 1. I'm gonna add this other piece in here of some of my test taking knowledge. Put it in quotes. Test taking wisdom. You guys notice how that last problem took a little while? So it took a long time. In the same time, we could have perhaps solved easier parts of the exam that were worth more points. So what am I saying? Study the exam right when you receive it. And start with the problems that will take the least amount of time. This will maximize the amount of points you get. Or at least maximize the amount of points you're able to try to get. Able to attempt. So come the final exam, if the first problem looks like it might be a long one, start with a different problem. It's another one of these things where I like to say that professors tend to be mean in some ways. They know exactly what sorts of things can trip you up, and they're going to try to do it because they want to see the students who don't get tripped up just as much. Okay, so let's move on to problem 2. Problem 2 says, once again it's in 2 parts, it has question 1. What is the integral of f prime of x divided by square root of f of x dx? It wants this written in terms of only f of x. That makes sense if we are performing the integral and it has an f of x on the inside. And initially looking at this, we want to ask ourselves, what is this problem trying to test? And the answer is not that crazy. It's indefinite integrals. And I guess here it's in a bit of an abstract sense. Right? Abstract in the sense that we're not working with x squared, we're not working with x cubed and so on, but we have this function sitting around that's just f, and so that's the abstract part. And so what sorts of tools do we have at our disposal? Well, we have u substitution and we have integration by parts. This starts to get a little bit intuition-y. You have to see problems a lot to really recognize which one you should or should not be using. Really, you have to decide between one of these. However, here's another little gem for you. If one technique runs into a dead end, try a different technique. Try the other. So I would say intuition-wise, you're going to want to try both of these. And if the first one you try doesn't work, switch to the second. It's slightly more common to have u sub problems. I'll say that. This is more common. So you should probably always start by thinking it's a u sub problem. Since it's more common, I would start here. Let's do that then. Let's see if we can decide what maybe this should be for a u sub problem. Let's write it down. And as always, let's make our lives easier. By simplifying before trying to integrate. Problems won't always look like you can integrate them right away. It's just something that you have to get used to. They're not going to look nice always. So we're going to rewrite this as f prime of x, f of x to the negative 1/2. I think that's what everybody would do to try to simplify this. We always like square roots as 1/2 powers. We always like denominators as negative 1/2 powers. And then I said, since we're going to try u sub, we'll try u sub first. So let's follow the priorities. For what u should be. This is important. Never forget these priorities. Priorities. U equals, the first priority is natural log of x if it exists. Does the natural log of x exist here? No, does not exist. So cross that out. Priority 2, denominator. If it exists. Does a denominator exist here? Yes, it does. Not after we simplified, it doesn't though. That's what I'll say. I'm going to say that the denominator doesn't after we simplify it, because if you simplify a problem, it's always going to, you're still going to be able to choose u correctly. So I would say you always simplify the problem and then go through your priorities. Don't work on the first step with the priorities, but rather simplify it and then go through your priorities. So priority 3 is e to whatever. Actually, it's the exponent. That's what I'll say. So u equals the exponent of e, if it exists. And do we have an e here? We do not. So that's gone. Priority 4 is whatever's in parentheses. And finally, we get something that exists. It does after we simplified. Since it does exist after we simplified, we're going to say, what was in our parentheses? F. That means that du is going to be f prime of x dx. That is indeed the derivative. And f prime dx exactly exists. This exists in the integral, so we're good to go. So we're good to go. And what does the integral look like then? Integral f prime of x, f of x to the negative 1/2 power dx is going to look like u to the negative 1/2 power du can integrate with the power rule to be u to the negative 1/2 plus 1 divided by negative 1/2 plus 1. And so that's u to the 1/2 divided by 1/2 equals 2u to the 1/2. What was u? U was just f of x. This is 2 f of x to the 1/2, or rather 2 square root f of x plus c. Does that look like the answer the exam gave us? And it certainly does. This is the answer. So since that's the answer that the exam gave, we're good to go. Part 2 of problem 2 says, well, I'll just write it out. Looking for the integral of r e to the a plus b r squared dA. This is another one written to trip you up. dA. So if I write a dA there, that means that the variable I care about, really the variable in my problem, is a, not r or b. Those are just constants. So this problem's not actually very hard once you recognize that. I'm going to say, can we simplify this at all? Can we simplify to make our lives easier? Yes, you almost always can. So we can simplify how exponential rules. What does this equal? Well, the r is just a constant in the integral. Oops. See, and I've almost made the same mistake. This should be dA. The r is just a constant in the integral. That can pull out. E to the br squared can also pull out. This is part of your exponential rules. Go ahead and look at the top of the exam to see that exponential rule. You can, the addition inside of the exponential is the same as multiplication outside of the exponential. And so they just pass right, the br squared term passes right through the integral sign. And all of a sudden, this is really written as integral a r squared dA, or I could write that as r e to the br squared integral. I'm going to write this as e to the r squared a dr. And we can, dr. See, this is as much of a problem as I'm having as you guys will. But they exist like this, so you have to get used to them. And then we can either follow this general exponential rule of integrals, that's at the top of the page, or you can do u sub. U equals r squared a. Either way, you end up with this term out front just hangs out front, but the other term turns into 1 divided by r squared e to the a r squared. And so if we simplify that, what do we get? We get e to the b r squared divided by, there was 1 r on top, 2 r's on bottom, you're left with 1 r on bottom, e to the a r squared. And we can go right back with our exponential rules and add the terms in the exponent together. E to the a is a plus b r squared divided by r plus c. And that's the answer the exam gave. There's the first two problems. Hopefully they weren't too bad. I'm just trying to test derivative rules for the first and integral rules for the second, even though I try to trip you up a little bit. Let's see if we can handle the third. Problem 3. Question. Well, it says, let s minus t squared equal t minus s cubed. What is ds dt? So this is implicit differentiation. That's what it's trying to test. Implicit differentiation. And so if you want, knowing this, you could just open up that lecture and work along, or you could try to remember how to do it. Let's just try to do this straightforward. See if we can do this. So what would go on here? We would take d of both sides. Follow our steps. Let's follow our implicit differentiation steps. I'm going to do this in blue. Step 1. Take d of both sides. Don't forget don't forget the chain rule is what I should say. Don't forget you have the chain rule giving d blank terms. So d variable terms. Right? This was a very big deal in implicit differentiation, that you would have these d variable terms. Step 2 is divide by d variable in the bottom of what we want to solve. Step 3 was bring all terms with what we want to solve to the same side. And all other terms to the other side. And step 4 was factor out what we want to solve. And then you divide by the rest. So these are our 4 steps for implicit differentiation. So we're going to follow those here. Let's do the first step. Take d of both sides. S minus t squared equals t minus s cubed. Let's do that. d s minus t squared, and we take d of t minus s cubed. This chain rule is going on here, right? This was step 1, though. I'm going to label this step 1. And the chain rules say, well, derivative outside, leave the inside the same, and then it's derivative the inside. This is really just d of s minus t on the inside. Here's 3 t minus s squared d t minus s. And d is nice, it just distributes. Right, these just distribute. So this really gives me 2s minus t dt, or ds minus dt. And this gives me 3 t minus s squared dt minus ds. Okay, step 2 says divide, in this case, by d of the variable in the denominator. What did I have in my denominator? I did dt, so I'm going to divide by dt. If I divide by dt here, I get 2s minus t ds over dt minus 1 equals 3 t minus s squared 1 minus ds over dt. Step 3, bring all terms with what I want to one side and everything else to the other side. So really, what do I have here? This is really, so I'm going to rewrite the above, is really ds dt times 2s minus t minus 2s minus t. Did not write that very well. equals negative ds dt 3 s minus t squared plus 3 s, or t minus s, both of these, t minus s squared. So I'm bringing all terms with a ds to one side and everything else to the other side. So my ds terms, I'm getting ds dt 2s minus t plus ds dt 3t minus s squared equals 2s minus t plus 3t minus s squared. It then says factor, this is step 4. Step 4, I factor this ds dt out. On the left, I get 2s minus t plus 3t minus s equals 2s minus t plus 3t minus s squared. This is squared there as well. And then I divide. Divide by everything that's not what I want to solve. So divide by 2s minus t plus 3t minus s squared. I divide by 2s minus 3 plus 3t minus s squared, and you guys are just like so mad at me right now because what's happening on the right? I hope you can see it. Boom, boom. When I cancel things, don't you guys dare forget this. When you cancel things, it's equal to 1. It's never equal to 0. It's equal to 1 when you cancel things. ds dt equals 1. And now you guys go back and look at the answer that the exam gives. And indeed, it's equal to 1. And so that's great. But we could have made our lives a lot easier. How? The answer to all questions of how in math is by simplifying. So what I started with, okay, we're in the right spot. Wait. I don't know where my note is. Oh, here we are. We're back. All right. Gosh, that was way too hard. Okay, by simplifying, what do we have? We have s minus t squared equals t minus s cubed. Well, what is t minus s cubed? That's just negative s minus t cubed. So if we have 2 of those on the left and 1 of those on the right, divide by s minus t squared. Okay, what do I get? Those cancel. This equals 1. That 3 cancels with those 2, basically, right? So I'm left up with 1. So I have 1 equals negative s minus t. What is negative s minus t? Well, that just says 1 equals t minus s. Or it's also saying s equals t minus 1. So ds dt is just the derivative of t minus 1 with respect to t. What is that? It's 1. Crazy how much easier your life could get if you simplify right away. So this is just another one of those things. The first thing you should always do, try to simplify your problem. So you simplify the problem as much as possible. Before starting. Really before starting the calculus. That's why we taught you how to do other math before we taught you how to do calculus. Hope that makes sense. Last problem for today, we're doing problem number 4. Problem number 4 says, you are buying J millions of jelly beans from the jelly bean factory. It had a cost of CJ. Cost of C of J equals 3 times 1 minus J squared dollars per J million jelly beans, valid for 0 less than J less than 1. You then move to Russia and are able to sell your millions of jelly beans at a revenue. So this is per J. That's what you want to think about there. It's the cost per J. You're able to sell at revenue R of J equals 1 minus J dollars. How many millions of jelly beans should you buy to maximize your profits? You want to read this as what should J equal? To maximize profits. So before we start, we want to take a step back and say, have I simplified this problem as much as possible? And is there anything that I might be missing before I start? Is it simplified as much as possible? I would argue, sure, it's fine. We then ask the question, though, am I missing anything? Well, the special thing here is that when I say this is the cost per J, if that's the cost per J, per million jelly beans we buy, the actual cost of buying J jelly beans is capital C is J times lowercase c. Or rather, this is equal to 3J 1 minus J squared. So that's kind of the one extra special step here. Now, when we're talking about maximizing profit, we need a profit function. You guys are thinking way back now to this one. P equals the revenue minus the cost. Your profit is equal to your revenue minus your costs. since the profit is equal to revenue minus cost, in this case, P of J of our jelly beans is equal to the revenue, 1 minus J, minus the cost C, 3J, 1 minus J squared. So I'll write this in one line here. This is revenue RJ minus CJ, capital CJ, not lowercase. Okay. So now that we have P, how do we maximize? And hopefully this is all coming back to you. It's an optimization problem. And all optimization problems are solved the same way. You take a derivative, set it equal to 0, solve for the variable. So we're going to do that. We're going to take a derivative, P prime. Well, that 1 drops out. We get negative 1 minus, ooh, looks like a product and a chain rule. Here's where simplifying might come in handy. We're going to simplify that. This is negative 3J. Well, what is 1 minus J squared? That's 1 minus 2J plus J squared. And so I could actually rewrite that even farther as 1 minus J minus 3J plus 6J squared minus 3J cubed. This is actually what I want to use when I'm taking my derivative. So if I take a derivative of that, I get negative J minus, or negative 1 minus 3 plus 12J minus 9J squared. And so I guess that's really like negative 9J squared plus 12J minus 4 equals 0. And then we'll just solve this with the quadratic equation, because I am not going to try to factor this. If something looks hard to factor, just use the quadratic equation. Something. I shouldn't say if something. If a quadratic looks hard to factor. Quadratic equal to 0 looks hard to factor. Use the quadratic equation. So we'll use the quadratic equation here. J equals negative b, so negative 12 plus or minus the square root of b squared, 12 squared, minus 4ac. 4a is negative 9, c is negative 4, all over 2a, all over negative 18. It's going to give me negative 12 plus or minus the square root of 144 minus 4 times 9 times 4 is 36 times, or sorry, it's, yeah, 36 times 4 is 144. What? Why would I do that? Over negative 18, there's a reason why I set these problems up the way I do for you guys. Negative 12 over negative 18, what do you know? It's 2/3. And that's the answer they gave. The answer the exam gives. Check. And that's that. I guess I'll see you all tomorrow with more of this. I hope this is making a lot of sense. Trying to spend an extreme amount of time on each of these, really talk through the theory, really talk through how to solve these problems. Anyway, have a good one. I'll see you tomorrow. We'll finish this exam then.